All right, we are in section 3.2. 3.2 is logarithmic functions. Logarithmic functions, okay? So we talked about exponential functions in 3.1, or I'm sorry, we're in 3.3, not 3.2. 3.3, okay, logarithmic functions. So we talked about exponential functions in 3.2, okay? And we learned a lot about exponential functions. We learned about their behavior, and now we're going to learn about logarithmic functions. And it turns out that logarithmic functions are the inverses of the exponential functions. So logarithmic functions are the inverses of exponential functions. They're inverses of each other. Okay? Logarithmic functions turn out to be inverses of the exponential functions. And we're going to learn how to find them and to work with them and look at their behavior, all this other stuff, just like we did for the exponential functions. Okay? First, we're going to start out with some simple things, though. We're going to look at some equations, and we're going to look at their solutions. And we're going to see why we need these logarithmic functions. Well, obviously, if I asked you 5 to the x, if I give you this equation, 5 to the x equals 5. 5 raised to the x power equals 5. And I ask you to solve that equation, right? 5 to the x power equals 5. Well, it's pretty obvious that the solution is x equals 1. If I raise 5 to the first power, x has to be 1. Okay? That x should be 1. But 5 to the x power, if I say 5 to the x power equals 20, well, now the question is not clear, because there is no integer power that I can raise 5 to and get 20. So I don't know the solution to this thing. Now this is called an exponential equation because I've got this exponential expression right here. This is an exponential term, right? That's what we learned in the last section. This is an exponential function. So this is an exponential equation. We're going to learn how to solve those in a later section in chapter 3. But I just don't know the answer to that. Again, I know that x is not an integer. There's no integer power that I can raise 5 to and get 20. Well, if I said that 5 to the x equals 25, well, this time you would know the answer, right? Well, the x must be 2. All right? Because again, there's an integer power, 5 to the second power. 5 times 5 gives you 25, so the x is 2. And we can continue this process. If I say 5 to the x equals 60, well, again, you wouldn't know how to answer that because there is no integer power of 5. There's no integer that you can raise 5 to and get 60, so I don't know how to answer it. And one more, 5 to the x equals 25. 125, rather. You know that x were 3. Because again, 5 times 5 times 5 gives you 125, and hence x is 3. Now, one thing we can conclude, if 5 to the first power is 5, and 5 to the second power is 25, then this x should be something between 1 and 2. It's not going to be a whole number. Won't be 1, won't be 2. But it's got to be a number somewhere between 1 and 2, because 5 to the first power is 5, 5 to the second power is 25. Same thing right here. This 5 to the x equals 60. I don't know what x is, but it definitely better be between 2 and 3. Again, 5 squared gives you 25. 5 cubed gives you 125. So 5 to the x equals 60. That x is a number somewhere between 2 and 3. We don't know exactly what it is yet. We will, but I know that it has to lie between the 2 and the 3. Okay? So these, again, are exponential equations, and we're going to learn how to solve them. But first, we're going to go ahead and continue our discussion of logarithmic equations. And we're going to have the definition first. Okay? I'm going to give the definition for a logarithmic equation. So if x and b are positive real numbers, x such that b is not equal to 1, okay, then y equals log to the base b of x is called the logarithmic function with base b. We just defined what we mean by the logarithmic function base b. And where, and this is the most important part, y equals log to the base b of x is equivalent to b to the y equals x. This is critically important. Okay? Y equals log to the base b of x is equivalent to b to the y equals x. You will have to know that expression to solve these. Okay? Again, I can't emphasize it enough. This will be critically important for us. This is called the logarithmic form. Or the log form. This one is called the exponential form. Okay? And you're going to have to be able to convert from one form to the other. They might give you logarithmic form, ask you to convert that to exponential form. They may give you exponential form and ask you to convert that to logarithmic form. But when you see one statement, you have the other. If I see this statement, y equals log to the base b of x, I can write that statement, b to the y equals x. If I see this statement in a problem, b to the y equals x, I can rewrite that as this. They are equivalent. They mean the exact same thing. If you have one, you have the other. So again, we're going to have to be able to convert between log form and exponential form. Okay? So, why did we need this? Why do we need this definition? Okay? Why do we need this definition of this logarithmic function to base b? Well, let's think about this for a second. If I have a exponential function, f of x equals b to the x, okay? And I ask you to find the inverse. Find the inverse, okay? Well, we had a four-step process for finding the inverse. The first thing was to rewrite f of x as y. Y equals b to the x. The next step, we would interchange the x and the y. So x equals b to the y. And the next step, we had to solve for y. Solve for y. That was the next step in that 4 or 5 step process for finding an inverse. You replace f of x with y, you interchange x and y, and then you solve for y, right? But the problem becomes, how do you solve this equation for y? How do I get that y out of the exponent? And before we learned this thing, there was no way to do that. There was no way to do that. If you got some expression that says 4 equals 2 to the y, I don't know how to get that y down. We don't have anything to do it. Now that I know that these things are interchangeable, if I see this exponential form, I can rewrite it as log form. Now I can say, since b to the y equals x, according to that, that's equivalent to y equals log to the base b of x. So this is my inverse. Again, this statement is equivalent to that one because of that rule. And now I was able to solve for y. And then the last step is to rewrite it in your inverse notation. Y is the same thing as f inverse of x. There's my inverse function. So knowing that definition and that equivalency is key to finding the inverse of an exponential function. Okay? I wouldn't have been able to solve for y without this statement. So that's why we needed to know this log function and its definition. And again, I cannot emphasize it enough. This statement right here, and I'm going to leave it written somewhere, y equals log to the base b of x is equivalent to b to the y equals x. That is key. And I'm going to leave that written on the board because we're going to use it in this whole section and probably for the next 2 or 3 sections. In some form or another, y equals log to the base b of x is equivalent to b to the y equals x. This is my notation for is equivalent to. It's just an error with, so it should be, that's what I use for is equivalent to, okay? So, let's see if we can use this statement and make sure that we understand how to go from log form to exponential form or vice versa. You should be able to do either one. So example 1, this is on page 382. Example 1. They asked us to write each equation in exponential form. Right? Each equation in exponential form. So, hey, they give me log to the base 2 of 16 is equal to 4. So they gave me log form. If you have that logarithm term, that means that they gave you the log form, and they're asking us to convert that log form into exponential form, okay? And I'm going to use this statement. So I've got this piece. Y equals log to the base b of x. So y equals log to the base b of x. So y is 4. The base b is 2. Log to the base b of x. X is 16. Y equals log to the base b of x. So now I want to convert it into that. B to the y equals x. B is 2 to the y to the 4th power equals x. That's the corresponding exponential form. You've got something with an exponent. Exponential form, you'll see an exponent. Log form, you'll see the word log. So log to the base 2 of 16 equals 4 means the exact same thing as 2 to the 4th power equals 16. They are equivalent statements. They mean the same thing. They're just written in different forms. One is in log form, one is in exponential form. B. B says log to the base 10. Log to the base 10 of 1 over 1,000, or 1 over 100, I believe. Yeah, 100, equals negative 2. Log to the base 10, 1 over 100 equals negative 2. So, y equals log to the base b of x. So y is negative 2. The base b is 10. Log to the base b of x. X is 1 over 100. It is perfectly fine that x is a fraction. X can be a fraction. Okay? That doesn't hurt a thing. Okay? So again, I'm going to write it in my equivalent exponential form, the base b, so 10, that's my base, to the y power, y is negative 2, so 10 raised to the negative 2 power is 1 over 100. And these are true statements. Take your calculator, 2 to the 4th power, 2 times 2 times 2 times 2, that gives you 16. Take your calculator for the second one, 10 to the negative 2 power is 1 over 100. C, log to the base 7 of 1 equals 0. Log to the base 7 of 1 equals 0. Log to the base 7 of 1 equals 0. So again, y equals log to the base b of x. So b, the base is 7, to the y power, 0, equals 1. That's the equivalent exponential form. Okay? So this is how we go from log form to exponential form. Example 2 does the opposite. Example 2, write each equation in, we went from log to exponential, so now we want to go to log form. Logarithmic form. Write each statement in logarithmic form. So this time A says 3 to the 4th equals 81. 3 to the 4th equals 81. Again, b to the y equals x, right here. B to the y equals x. So the x in that case is 81. The base is 3. Y is 4. So y is 4. So y equals log to the base b of x. So the y is a 4 equals log to the base b. The base was 3 of 81. Okay? Y equals b to the y equals x. Y equals log to the base b, 3 of 81. Those statements mean exactly the same thing. Okay? And b was 10 to the 6 equals a million. B, 10 to the 6 equals 1 million. Okay? B is 10 to the y is 6, equals x. X is 1 million. All right? B to the y equals x. So now y was 6, equals log to the base b. B is 10 of a million. That would be my equivalent log form. Okay? Finally, 1/5 to the negative 1 equals 5. C, 1/5 to the negative 1 equals 5. Okay? Again, b to the y equals x. B is 1/5. Y is negative 1. X is 5. B to the y equals x is equivalent to y equals log to the base bx. So b to the y is negative 1. Log to the base b. B was 1/5, right, of x. Now, it does not matter if you write this like this, or I could write it like this. It's equality. They mean the same thing. If one thing equals the other, it doesn't matter about the order that you write that in. That's the exact same statement. So don't get caught up in that. Okay? So this is how we get from log to exponential form, or from exponential form to log form. Okay? And again, it comes from that equivalency. I can't emphasize that enough. You have to know that equivalency. And if it helps you out, write down what y, b, and x are. Then use that equivalency. Once you've done 4 or 5 of these things, then you'll know how to do it. You won't have to write them down anymore properly. Okay? But this is how we do it. Nothing hard about it if you know that equivalency. If you know that equivalency, this is not a difficult process. Okay? Well, now we're going to learn how to evaluate. Evaluate logarithmic expressions. So now I know a little bit about these log expressions. Okay? Well, sometimes I'm going to have to evaluate them, and sometimes I'll be able to simplify them. Okay? Sometimes when I convert from one form to another, I'll see that I can simplify. When I can, I have to. It is always your job to simplify as much as you can. Okay? Well, before we do that, they give us the equivalence property of exponential equations. The equivalence property of exponential equations. And this is on page 383. Again, make sure you're reading your book. I'm not going to do everything in this book, so it is critical that you read your book and fill in the blanks. I do all the stuff that I think is important, but it's your job to read and fill in the blanks. Okay? They say if b, x, and y are real numbers, b greater than 0, b not equal to 1. I'm not going to do that. I'm going to say look at preconditions. Okay? Again, it said b, x, and y are real numbers, b greater than 0, b not equal to 1. What the rule says is b to the x equals b to the y means that x equals y. Okay? So whenever I have two exponential expressions with the same base, that's key. That b is the same. The base has to be the same. When b to the x equals b to the y, then x has to be to the y. But again, the base must be the same number. Whenever the base is the same, and they're raised to different powers, well, that just means that those powers turn out to be the same thing anyway. That makes sense. That's a pretty logical progression. If b to the x equals b to the y, then the x must be equal to y. So with that in mind, example 3, evaluate. Example 3, evaluate. So they give us a log to the base 4 of 16. Log to the base 4 of 16. Okay? Log to the base 4 of 16. Well, if you want to, we've been doing these y equals log to the base b of x. So log to the base b of x, and I'm going to say it's equal to some y. That's perfectly fine. And I'm trying to figure out what the y is. I'm trying to figure out what is log to the base 4 of 16 equal to. So I'm going to call it y. So again, y equals log to the base b of x. And because I know I can use this equivalency, y equals log to the base b of x. So the base is 4, x is 16. So now I can turn that into this thing. B to the y is x. If I have this statement in log form, I can rewrite it in exponential form as b to the y equals x. Well, all you got to do is ask yourself, 4 raised to what power is 16? Well, y must be 2. So hence, log to the base 4, 16 is 2. So I can evaluate that log expression. Okay, I can evaluate that log expression. Log to the base 4 of 16 equals 2. Now, once you clearly understand this equivalency, y equals log b to the x is equivalent to b to the y equals x. All you ever got to ask yourself is, okay, 4 raised to what power gives you 16? Because I didn't know what this was. I was trying to figure out, okay, what is this equal to? Well, when I see this expression, what you ask yourself is 4 raised to what power gives you 16? Well, it better be 2. So you don't have to set this up as equal to y if you don't want to, but you can, okay? So we've evaluated that expression. B, log to the base 2. So B, log to the base 2 of 8. Log to the base 2 of 8. So again, log to the base b of x equals some number y. Well, if that is equivalent to b to that power, y equals x. So all you got to do is ask yourself, I'm trying to figure out what this is equal to. Well, what you're asking yourself is 2 raised to what power is 8? That's all you're asking yourself. You're converting from log form to exponential form. And again, if you want to call this y, that's perfectly fine. We'll call it y. So y equals log to the base b of x is equivalent to b to the y equals x. And again, all you're saying is 2 raised to what power gives you 8? Well, y better be 3. 2 to the 3rd power. 2 times 2 times 2 is 8. Okay? So we can evaluate these log expressions. Log to the 1/2 of 8. C says log to the 1/2 of 8. Well, again, if you want to call that y, then b, the base, so some power y is equal to 8. And what you have to ask yourself is, what does that power have to be? Well, I got to be a little careful this time. I'm taking a fraction, raising it to some power, and I want to get 8. Well, I don't know. Let's say y equals 4. Okay? Well, let's say 3. Suppose y were 3. I'm guessing. I'm going to guess that y is 3. Okay? So y was 3. I'd have 1/2 to the 3rd power. Well, that means 1 to the 3rd over 2 to the 3rd. That's 1 over 8. So I'm getting a number I want 8, but the problem is it's in the denominator instead of the numerator. Because I just want 8. I want whatever y is, the correct answer. I want to get this 8, but if I put a positive 3, I get 1/8. So what if I put a negative 3? What if I put a negative 3? Let's see what that does. 1/2 to the negative 3 power. Anytime you've got a fraction to a negative exponent, you can flip the fraction over and the exponent changes sign. That is a rule of exponents. Anytime you have a fraction raised to a negative exponent, if you flip the fraction over, the exponent changes sign. So 1/2 to the negative 3 power is equivalent to 2 over 1 to the positive 3 power. And now you get 2 cubed over 1 cubed. Well, that's positive 8. So it must have been 1/2. Or it must have been, I'm sorry, negative 3. So sometimes these exponents will be negatives. Okay? Sometimes these exponents will be negatives. All right, so this is how we evaluate these log expressions. And I've been using this equivalence property for these exponential equations. Okay? Definition of common and natural logarithmic functions. Definition of common and natural logarithmic functions. Well, we know what log functions are now. We know what log functions are now. But it turns out that there are two special ones, okay? And a log function is pretty much defined by the base, okay? A log function is defined by the base. For example, right here, log to the base 4 of 16, there's my base. The base equals 4. Log to the base 2 of 8. The base equals 2. Right there, the base was 1/2, right? Remember when we defined these log functions, the base had to be greater than 0, and it couldn't be 1. So it can be a fraction between 0 and 1, right? The base is 1/2. Or it can be a number bigger than 1, 2 or 4, okay? So for a log function, all right, the base is the biggest determining factor for the behavior of that function, all right? Well, so we're talking about definition of what? Common and natural logarithmic functions. And this is on page 384, make sure you read it. Again, I'm going to paraphrase, so make sure you read this carefully. The log function base 10, so logarithmic function with base 10 is called a common logarithm. Okay? The logarithmic function that has base 10 is called a common logarithm. And when you see, like right here, I wrote base 4, I wrote base 2, I wrote base 1/2. Okay? But it turns out that y equals, when you just see log of x, okay, that is the common logarithm. It actually means log to the base 10 of x. But if it's base 10, I don't have to write it. It's assumed to be a 10. So on your calculators, you have a log x key. On your calculators, you should have a log x key. Well, that means log to the base 10 of x. Base 10 is the only one. If you don't see a logarithm, if you don't see that little log written, then it's assumed to be the common logarithm base 10. Okay? So y equals log x means y equals log to the base 10 of x. That's the only one that you don't have to write the base. If it's anything other, if the base is something different than 10, it has to be specified. You have to say log to the base 4 of 16, log to the base 2 of 8, log to the base 1/2 of 8. If the base is anything other than 10, it must be written. If it is a log base 10, you don't have to write it. It's called y equals log x. It's assumed that everybody knows that that's base 10. Okay? That's called the common logarithm. Okay, this is called the common logarithm. So again, there's a log x key on your calculator, and that's the one you're going to use when you calculate the common log. Okay? The logarithmic function, the log function with base e. Remember e from when we did these exponential functions in the last section? E is 2.718, etc. Okay? That is called the natural log. It's called the natural logarithm. Okay? So that one is y equals ln of x. Now, y equals ln of x is equivalent to log to the base e of x. You're not going to see that, but that's how they're going to write it. But it means log to the base e of x. Okay? So on your calculator, you also have a ln x key. ln of x key. That means the natural logarithm. The natural logarithm is nothing more than the log base e. The common logarithm is nothing more than the log base 10. They're the only two logarithms that have special considerations and special names. Any other log base 2 of something, log base 5 of something, etc. But common logarithm means log base 10, y equals log of x. Natural logarithm means log base e, y equals ln of x. So you use that y equals ln x key on your calculator to calculate the natural logarithm. You use that y equals log x key on your calculator to calculate the common logarithm. Okay? And everything we've talked about for logs, using that conversion and everything, it still works for the common log and the natural log. Okay? But you just have to again remember, the common log is base 10, natural log is base e. So with that in mind, let's look at some of these common and natural logs. Example 4. Example 4, they say evaluate. So A says log of 100,000. Log 100,000. Well, since they didn't specify the base, that means it's the common logarithm. That means we're calculating the log base 10. They didn't write a base, so it's assumed that that is a log base 10 calculation. So again, we've done these. All you're asking yourself is, we're trying to figure out, okay, what is that equal to? I know that my base is 10. So all you're asking yourself is 10 raised to what power is 100,000? Okay? That's all you're asking yourself. 10 raised to what power is 100,000? Take your calculator, you've got 1, 2, 3, 4, 5 zeros. 10 to the 5th is 100,000. So that thing is equal to 5. 10 to the 5th power gives you 100,000. So log of 100,000 is equal to 5. B says log of 0.001. Log of 0.001. Well, again, they did not specify the base. So again, that's a common log. That's log base 10. Well, I'm trying to figure out what that's equal to. So again, you're asking yourself, 10 to what power is 0.001? All right? Well, now, 1, 2, 3. If you move your decimal place 1, 2, 3 places, you'll get 1. Okay? So this should be negative 3. 10 to the negative 3 power is 0.001. Take your calculator and try it. Okay? Take your calculator and try it. All right. That's fine. C says ln of e to the 4. C, ln of e to the 4. Well, again, natural log means log base e. So I'm trying to figure out what is this equal to. So again, this is log base e of e to the 4. If you wanted to look at it, log base e of e to the 4 equals what? This statement is exactly that. When you see ln, that means log base e of that thing. So your question you ask yourself is the base raised to what power gives you e to the 4? Remember, b to the y equals x. You're converting from log form to exponential form. B to the y equals x. My base is e. I'm trying to figure out what y is. B to the y equals x. And clearly, it better be 4. Okay? It better be 4. And finally, ln of 1 over e, d. ln of 1 over e. Okay? Again, ln means log to the base e of 1 over e. So we're trying to figure out what that is. So again, the base is e. So e raised to what power is x. B to the y equals x. So e raised to what power is 1 over e? Well, it better be negative 1. Negative 1. Okay? So this is how we This is the same stuff we were already doing, but we're doing it now with both this common and this natural logarithm. That's the difference. We're exploiting those same rules. We're evaluating these logarithmic functions, but now we're considering these common and natural logarithms. Okay. They say, again, you have a key for the common logarithm and for the natural logarithm on your calculator. Okay, you have a key for the common logarithm and the natural logarithm on your calculator. So example 5 exploits that. Example 5, they asked me to approximate the logarithms. Approximate the logarithms. Hey, so they say log of 5,809. Okay? Well, I don't have a choice. Okay, again, log means log base 10, that's the common log. So I want to know what this is equal to. So again, I can use that. My base is 10, so b to the y equals x. So you'd be asking yourself, 10 raised to what power is 5809? Well, I don't know, because that is not, this thing is not a power of 10. Okay? So I can't figure that out in my head anymore. But I have a log key. So on your calculator, take the log, y equals log x key of 5809, and you'll get a decimal. They say you'll get 3.764, and it's rounding, so 3.764, 101,376. So you're going to have to use a calculator to approximate a lot of these things. Okay? You won't be able to do them without your calculator. B says log of 4.6 times 10 to the 7th. All that means is 4.6 times a 1 with 7 zeros. Right? I think, what's that, 46 million maybe? 4.6 times a 1 with 7 zeros. Okay? And they say that you'll get 7.66275, and that's all I'm going to write, 7.66275, ... Again, you're just plugging these into your calculator. All right? So you can look at C, D, and E. Okay? You can look at C, D, E, and F, because it's nothing more than plugging it into your calculator. I'm not going to do any more of those. All right? The next thing we're going to talk about is basic properties of logs. Basic properties of logs. Basic properties of logarithms. I'm going to just say logs. Basic properties of logs. Okay. So, number 1, they say that log to the base b of 1 equals 0. Log to the base b of 1 equals 0, no matter what the base. If that base is 10, log of 1 equals 0. If that base is 2, log to the base 2 of 1 is 0, etc. The base can be anything. And they say because b to the 0 equals 1. So they convert it to exponential form using this. Y equals log to the base b of x. Means b to the y equals x. So b to the 0 equals 1. So this is true because of that. You're using that equivalency. Number 2, log to the base b of b. Log to the base b of b is equal to 1. Okay? And again, this is because b to the 1 equals b. Again, using that equivalency. Log to the base b of b is 1 because b to the 1 equals b. The third property of logs. Log to the base b of b to the x. Okay? Log to the base b of b to the x is x. Because b to the x, b to the y, this is y now. Log to the base b of x equals y. Log to the base b of x, all of that, equals y. only if b to the y equals x. Okay? Hopefully these are making sense. B to the log base b of x equals x. B to the log to the base b of x equals x. Okay? Now this time they gave me the exponential form. So the base b is b, y is all of that. B to the y equals x. Okay? Because, and I'm going to convert this to log form, because y equals log to the base b of x. Y equals log to the base b of x. Okay? So this one they gave me exponential form, and I use that exponential form to convert it back to log form. 5 log to the, and they gave me examples of all of these. These are my problems. There's only 4. Okay? Let's do an example that will illustrate some of these properties. They do an example beside each one. I'm just going to do the examples out of the book. You can look at those that they did. So example 6, simplify. Example 6, simplify. Hey, log to the base 3 of 3 to the 10. Log to the base 3 of 3 to the 10. Log to the base b of b to the y. Log to the base b of b to the x, rather, I'm sorry. Log to the base b of b to the x, well, coordinate is equal to x. Log to the base b of b to the x, that'll be x. So I'm exploiting property number 3. Okay? I'm exploiting property number 3. Okay? And that's all you're doing. You're just trying to figure out what form does it fit in terms of which property you use. B, ln of e squared. Ln of e squared. Ln of e squared. Again, ln is log to the base e. Log to the base e of e to the x. Okay? Log to the base b of b to the x. So we're still using him. ln means log to the base e. So log to the base e of e to the x. Log to the base b, b to the x, better be 2. Okay? Better be 2. All right. C, log to the base 11 of 11. C, log to the base 11 of 11. Log to the base b of b equal to 1. Because of property 2. D, they say log of 10. Log of 10. Well, log of 10 means common logarithm. So log to the base 10 of 10. Log to the base b of b, still 1. Property 2. Okay. All right. E, log to the square root of 7 of 1. That's kind of cool. Log to the base square root of 7 of 1. So log to the base b of some x. Okay. Log to the base, yes. That is, yeah, log to the base square root of 7 of 1. Oh, yeah. Right here. Log to any base of 1 is 0. Log to any base of 1 is 0. Property number 1. Property number 1. F, they say ln of 1. Again, ln means log to the base e. And again, log to any base of 1 is 0, according to property number 1. Log to the base e of 1, log to any base is 1, according to that property. G says 5 to the power log base 5, c squared plus 4. Log base 5, c squared plus 4. 5 raised to the log to the 5 base 5 of c squared plus 4, well, that's this thing. My base, in this case, b is 5. So b raised to the log base b of something, b raised to the log base b of something, is that thing. So I get c squared plus 4. I get c squared plus 4. And finally, 10 to the log of a squared plus b squared. 10 to the log of a squared plus b squared. Well, a base raised to the log base of something, still that property is x. So I'll get a squared plus b squared. So that's how we use those properties. Okay? That's how we're going to use those properties. Okay? All right. So nothing hard about that. And again, you just got to know those properties, learn those properties, or have them close on a sheet so that you'll be able to use them. All right. Next thing they talk about is graphing log functions. Graph log functions. Graphing log functions. Okay. Well, excuse me. So they say that let's just do one. Let's just do one. Now I said a couple of things when we started. I said when we started this section, the exponential function and the log function are inverses of each other. The exponential function and the log function are inverses of each other. So what that means is example 7, graph. They say 8. They say y equals log to the base 2 of x. Y equals log to the base 2 of x. I want to graph that function. Okay. Well, so again, I know that y, and again, I know this equivalency. Y equals log to the base b of x is equivalent to b to the y equals x. So this is equivalent to 2 to the b to the y, equals x. Okay? So really, this function and this function are inverses of each other. Those two functions are inverses of each other. Y equals log to the base 2 of x is the inverse of y equals 2 to the x. So let's just get some points. We graphed this one before. When x is 0, 2 to the 0 is 1. When x is 1, 2 to the first power is 2. When x is 2, 2 to the second power is 4, right? And I can keep going. Let's do some negative. 2 to the negative 1. 2 to the negative 1 is 1 over 2. So 2 to the negative 1, 1 over 2 to the positive 1 equals 1/2. When it's negative 2, 2 to the negative 2 is 1 over 2 to the positive 2. That's 1/4. So these are the points for y equals 2 to the x. But since I know that this function and this function are inverses of each other, for this function, the points, that's the beauty of inverse functions. If I understand how a function and its inverse operate, an inverse function is the exact opposite of the original function. So if I know the points on the original function y equals 2 to the x, to get the points on the inverse function y equals log to the base 2 of x, all I do is flip coordinates. Instead of 0, 1, I'll have 1, 0. Instead of 1, 2, I'll have 2, 1. Instead of 2, 4, I'll have 4, 2. Instead of negative 1, 1/2, flip it over, 1/2, negative 1. Instead of negative 2, 1/4, 1/4, negative 2. Those would be the points on the inverse function y equals log to the base 2 of x. So, let's graph it. X, y, 1, 2, 3. 1, 2, 3. Okay? 1, 0, right here. 2, 1, over 2 up 1, right here. 4, 2. Over 4, up 2, right here. Negative 1/2, negative 1, go over 1/2, negative 1, right here. Okay. 1/4, negative 2, 1/4, negative 2, right here. So I clearly see the behavior of this function. So this is y equals log the base 2 of x. Now again, y equals 2 to the x. These points, 0, 1, 1, 2, 2, 4, negative 1, 1 half, negative 2, 1 fourth. This was y equals 2 to the x. And we had talked about before how a function and its inverse, their graphs, the graph of one, if you flip across the line y equals x, will give you the graph of the other. That's how functions and the inverses operate. Okay? So we can clearly see that y equals 2 to the x and y equals log to the base 2 of x are inverses of each other. So when I want to graph one of these log functions, because your calculator only knows how to do base 10 logarithmic functions and base e logarithmic function. You got a log x key and you got a ln key, right? That's base e, that's base 10. So when they talk about base 2, you can't do that on your calculator. So what you're going to have to do is you're going to have to graph the inverse function or get the points for the inverse function y equals 2 to the x, flip those points, and then you'll have points for y equals log to the base 2 of x. Okay? So that's how we're going to graph these log functions that don't have base 10 or base e. If I ask you to graph a common log or a natural log, you can use your calculator to just get points. Take an x equals 1, plug it in your calculator. Take x equals 5, plug it in your calculator. But if it's base 2, we don't have that luxury. Your calculator only knows how to do base 10 and base e arithmetic. So that's how we're going to graph these log functions. So there's y equals log to the base 2 of x. Okay? I'm going to get rid of this part. I just wanted to illustrate that and make sure it was clear how that worked. Hopefully it is. So there's y equals log to the base 2 of x. I also want to graph part B, and I'm going to use that same graph. They say y equals log to the base 1/4 of x. Okay? I'm also going to graph y equals log to the base 1/4 of x. Well, it's the same idea. I'm going to consider y equals 1/4, to the x. This is the inverse function for him. Okay? And let's get some points on it. When x is 0, 1/4 to the 0 power is 1. When x is 1, 1/4 to the first power is 1/4. When x is 2, 1/4 squared, 1 squared gives you 1, 4 squared gives you 16. When x is negative 1, 1/4 to the negative 1. Anytime I have a fraction to a negative power, I can flip the fraction over, the power changes to a positive. That's 4. Okay? Negative 2, 1/4 to the negative 2. I've got a negative exponent, flip the fraction over, exponent changes to positive. That's 16. So not hard to get points on this inverse function. Okay? Well, again, points on this function. Once I know these points, all I have to do is swap coordinates, and then I have points on y equals log to the 1/4, base 1/4 of x. So instead of 0, 1, 1, 0. Instead of 1, 1/4, 1/4, 1. Instead of 2, 1/16, 1/16, 2. Instead of negative 1, 4, 4, negative 2. Instead of negative 2, 16, 16, negative 2. Okay? So now, let's plot those points. 1/4, comma 1. I'm just using this graph. So x is 1/4, y is 1. Okay? 1, 0, right here. 1, 0. 1/16, 2. 1/16, 2. Okay? 4, comma negative 2. 4, negative 2. 16, negative 2, way out there, right? So you clearly see this is 1/4. 4th to the x. They both go through the point 1 comma 0. Okay. So I claim that if you understand those two graphs of log functions, then you now understand how the graph of any log function will look. Every log function will look like one of those two graphs. It'll be very, very similar to one of those two graphs. So let's just recall when we looked at the last section, okay? When we looked at the last section, these exponential functions, we said that all exponential functions, so exponential functions, okay? When we did those graphs, and we had all these nice properties, we said all exponential functions will either do this. This is when b was greater than 1, right? F of x equals b to the x. B greater than 1, they all cross right here, 1, right? And when b was less than 1, it would be a decreasing function. So this was b greater than 0, less than 1, f of x equals b to the x. They'd all be decreasing. That's how exponential functions work. So now with that same idea, logarithmic functions. And this chart is on page 388. Page 388. Make sure you take a look at it carefully. Okay, so this time, the graphs of all log functions, well, they all go through the point instead of 0, 1, 1, 0. All logarithmic functions go through the point 1, 0. All exponential functions go through the point 0, 1. Okay? Well, just like we see there, if the b is greater than 0, all log functions will do that. It'll be an increasing function like that. If the b is less than 0, or not less than 0, but greater than 0, less than 1, it'll do that. Okay? It'll do that. So just like before, all exponential functions, when b is greater than 1, is an increasing function like that. All exponential functions, when b is greater than 0, less than 1, is a decreasing function like that. Now we know that all log functions, where the base is bigger than, not 0, but bigger than 1, when the base is bigger than 1, it does this. And when the base is bigger than 0 but less than 1, it does that. Remember, the base has to be positive and it can't be equal to 1. When we defined exponential functions, we said the base had to be positive and it can't be equal to 1. Okay? So all log functions will do that just like all exponential functions do that. Okay? And so we can talk about the domain. And if we remember, that's the beauty of knowing these functions. For this function, these exponential functions, the domain was everything. The range was from 0 to infinity. So for log functions, the domain is now from 0 to infinity. The range is everything. They flip, right? The domain for this function, since he's the inverse, becomes the range. The range for this function, since that's the inverse, becomes now the domain. So the domains and range flip for exponential versus logarithmic functions. That makes sense. They're inverse functions of each other. Okay? Horizontal asymptote. There was a horizontal asymptote, y equals 0. Now we have a vertical asymptote. For the inverse, x equals 0. Again, they're inverses of each other. That makes sense, right? Everything here passes through 0, 1. Over here, everything passes through 1, 0. Okay? Over here, if b was greater than 1, it's increasing. is greater than 1, it's increasing. Over here, b greater than 1, increasing. Okay? That's the one thing that holds. And the same thing for decreasing. If b is between 0 and 1, decreases, b between 0 and 1 decreases. So those are only two properties that don't flip. But everything else flips. So there's the behavior of exponential functions, there's the behavior of logarithmic functions, okay? Just like before, you could use these transformations. Just like we looked at those transformations for the exponential functions, they can be transformations for these log functions. I can have horizontal and vertical shifts, okay? So if I have this graph, y equals log to the base 2 of x, right? If I wanted to graph g of x equals log to the base 2 of x plus 1, right? X plus 1. Do it in red. If I wanted to graph g of x equals log to the base 2 of x minus plus 1. Well, all that does is slide this graph back 1 unit, and the old horizontal, old vertical asymptote of 0 becomes this. This point moves over to here, so that would be that graph. So I can still have the horizontal and vertical translations, that still holds. So that's example 8. I'm not going to do that. You can look at it. I think it's not hard to figure out. Okay. I'm going to do example 9. I'm going to do example 9. Now we see, these are my logarithmic functions. We see these graphs. These graphs begin at x equals 0. So really important, the domain of log functions is 0 to infinity. I can't take the log of 0, okay? X equals 0, the y-axis is a vertical asymptote. Vertical asymptote, x equals 0. So the domain of log functions goes from 0 to infinity. So I can't put anything smaller than 0 into any log function. So with that in mind, example 9, write the domain. Write the domain. So A says f of x is log to the base 2 of 2x plus 4. Log to the base 2, 2x plus 4. Log to the base 2 of 2x plus 4. So again, that's a log function. So the domain is from 0 to infinity. So whatever you're trying to take the log of, that has to be a greater than 0 quantity. So 2x plus 4 has to be greater than 0. That's the only way I'll be able to take the log of it, if it's positive. Okay? So let's solve this inequality. Subtract 4 from both sides. Divide by 2. Okay? X greater than negative 2. So the domain, they wanted it in interval notation, is from negative 2 to infinity. The domain of that function would be from negative 2 to infinity. Next is g of x equals ln of 5 minus x. G of x equals ln 5 minus x. Again, that's a log. The stuff you're trying to take the log of has to be greater than 0. Okay? So subtract 5 from both sides. That says that negative x greater than negative 5. I don't want negative x, I want a positive x, so divide by negative 1. When you divide by a negative, the inequality changes from greater than to less than. So x less than negative 5 over negative 1 is positive 5. So the domain of him equals, everything less than 5 will be from negative infinity to 5. Okay? From negative infinity to 5. Okay? C. There's one more. C. C says h of x is log of x squared minus 9. H of x is log x squared minus 9. Okay, h of x is log of x squared minus 9. Now again, same principle. Domain of logs, only positive quantities. You can only take the log of a positive quantity. So you've got to make sure the stuff you're taking the log of better be greater than 0. Okay, the stuff you're taking the log of better be greater than 0. Okay, well, this one's a little more tricky. You're trying to find where your product. Factor this and you'll get x plus 3, x minus 3 greater than 0. Remember when we did those inequalities back in chapter 1 or 2, I can't remember. In 171, these things, we had to do a little chart. Because we're trying to figure out where something times something is greater than 0 or positive. So you're trying to figure out where something is positive. So set it equal to 0. This gives us our boundary points. So x equals negative 3 is the 0 here. X equals positive 3 is the 0 here. So negative 3 and positive 3 separate the real numbers line into 3 intervals. There's negative 3, there's positive 3. Now, the product is equal to 0 there. That's where this thing is equal to 0. Now, I'm trying to figure out where this product is greater than 0. But again, these two boundary points separate the real number line into 3 intervals. The first interval is from negative infinity to negative 3. That's from here to there. Then between here and here, negative 3 to 3. Then from here to there, 3 to infinity. So what I'm going to do is I'm going to investigate that product, and I'm going to figure out the sign of that product in each one of those respective intervals. Okay, I want to figure out if that thing is positive or negative in each one of those respective intervals. Okay. Well, so we write those intervals down. Negative infinity, negative 3, negative 3 to 3, 3 to infinity. Okay. We're going to need a test point in each interval. So we're going to make a chart. Hopefully this is somewhat familiar. Okay. I'm going to make a chart. So we're going to do the test point in each interval. We're going to look at x plus 3 in the interval. We're going to look at x minus 3 in the interval. Then we're going to look at the product. Okay? We'll look at x plus 3, x minus 3, then the product. So a test point in that interval might be x equals negative 4. A test point inside this interval might be x equals 0. You can use any number you want. In this interval, x equals 4. All you're doing is choosing a point, a value of x that's in that interval. Okay? So now all you're going to do is you're going to plug that test point into each expression. So where you have an x, put a negative 4. Negative 4 plus 3 is a negative 1, so that's a negative quantity. Next interval, x equals 0. 0 plus 3 is a positive 3, that's a positive quantity. All I want to know is the sign. I don't care what number it gives me. I just want to know is it positive or negative. X plus 3 in the interval from 3 to infinity, use the test point 4. 4 plus 3 is a positive 7, so that quantity is positive. So this expression, x plus 3, is negative in that interval. X plus 3 would be positive for any number in that interval, and x plus 3 would be positive for any number in that interval. Do the same thing for x minus 3. Use the test point negative 4. Negative 4 minus 3 is negative 7. So this expression is negative for any number in that interval. Choose the test point 0. 0 minus 3 is negative 3. So this expression is negative in that interval. Take the test point 4. 4 minus 3 is a positive 1. So now that expression is positive in that interval. Well, I wanted to know what the product did. Well, now I got it. In this interval, this expression is negative, this is negative. So a negative times a negative, because I'm multiplying this times this, a negative times a negative makes this product a positive. In the interval from negative 3 to 3, a positive times a negative gives me a negative. In the interval from 3 to infinity, a positive times a positive gives me a positive. So what did I want to know? I wanted to know where the product was positive. Well, the product is positive in the interval here. That product is positive in the interval here. So the solution would be from negative infinity to negative 3 union that interval. 3 to infinity. That would be my solution there. That's because I had a quadratic inequality. So they're a little bit more work. Okay, they're a little bit more work. Okay? I'm going to leave example 10, read it, see if you can do that. I'm going to leave example 10 to you. If you have any questions, I will be glad to do that problem and post it, but I want you to try it first. Thank you.